thanks for this opportunity to speak here and for this workshop happening. So yeah, the title is cut and paste invariants like K-theory. And the plan for today would be I will spend few minutes to talk about 200 years old things which served as a motivation for the whole story. Then I will pass to the part how this very old story for polytopes and polygons has an analogy for manifolds, which are called SK groups, and they were invented here in Bonn, like 30, 40 years ago. Then we will discuss a version of K-theory, which is more general than Walthausen's K-theory, and then that will allow to construct a spectrum out of category of manifolds. So category of manifolds is not Walthausen category, but we will make it nice enough so that it fits into some machinery of K-theory. Then I will proceed how to connect these two parts together, so this SK invariants, cut and paste invariants of manifolds, and this construction of K-theory. And then I will proceed with K-cube construction. So let's start with a very classical story. So classical scissor conference. And imagine we are working on a plane, R2, and we're working only with polygons. And we have to pair scissors, and we do the following thing. We start with some polygon. It can be, it shouldn't be convex, it shouldn't be connected. We cut it using our scissors, and we paste it back somehow such that pieces don't overlap, only touch along the edges. And we call it a cut and paste operation. So if we start with some polygon and we do finitely many cut and paste operations, we arrive at some other polygon and we call such two things scissor concurrent. And obviously when we do such an operation, we preserve area. And the question is it the only thing that is preserved? And the answer is yes. So if you have two polygons of the same area, then you can pass from one to another by finitely many cut and paste operations. And then in 1900, Hilbert apparently also liked this question. And so the famous,
like an R2?
It's on R2, in
yeah.
R2, yes. And Hilbert decided, like, what do you do in R3? So in R3 you can do all the same, but now you cut not using scissors but some planes. And you ask yourself, is the volume the only thing that is preserved? Volume is the only thing that distinguishes two such polyhedra. And the answer is no. So in R3 there is one more invariant, which is then invariant. And the answer in R3, there are two invariants, it's volume and so-called then invariant. And usually I spend too much time on then invariant, so I will not introduce it today. And then actually things got more complicated when you go in higher degrees. So let me leave some traces on the blackboard. So for n equals 2, meaning that we are working in R2, area was our only invariant. In n equals 3, it was volume and something that's called then invariant. And let me just tell you where this lives. So volume is some number, and then invariant is something that lives in the tensor product of R and R mod Z. So in the end, if you have time, I will tell you, it's super interesting. And in higher dimensions, one can also ask the same question. And there are also then invariants in higher dimensions. So for n at least 4, we also have higher than invariants. And it is an open problem, I think, starting from 5 is volume and then invariants, everything that classifies cut and paste classes in Rn. But there is even more complicated thing that you can do. You can study a group. So Caesar congruence group in Rn is an abelian group with generators given by polytopes in Rn. And then you quotient out by saying that sum is given by disjoint union, and you mod out also Caesar congruence relation. And on the first glance, it is very similar to the previous question, so to classifying the invariants, but actually this is one step more difficult. So let's see, for example, y in n equals 3. So you have volume, and you can map from R to Caesar congruence group in dimensions of 3 by sending any number to cube of the corresponding volume. And then you have this then invariant D, which lands somewhere. And you might think that the answer that the group is just direct sum of R and this expression. But the problem is that this then invariant, it doesn't have to be surjective, so it has some cokernel. And this cokernel is usually quite difficult, and it is expressed in terms of K-theory. And this is a whole general motivation how two people, which were Zakharevich and Campbell, so they thought if you have this exact sequence, you have these Caesar congruence groups, and somehow K-theory appears. Why don't we try to cook up some category and some construction of K-theory that dares to be called K-theory, such that you can see all this map on the level of categories. So it's like internal properties of some category that produces this kind of maps. And unfortunately, so this was the motivation. I don't think that they exactly achieved this goal of constructing precisely some nice category and K-theory machinery so that you can see all of that. But at least they tried and obtained some other nice results. So let me write that Zakharevich and Campbell, and actually independently, they were looking for some construction of K-theory, and they have different. Let me put it like this. Let's say to explain nature of some maps. Okay, so here we stop with this classical part, and we will just take an inspiration and some of these machineries from this story. So we will actually talk about manifold setup, not polytopes, and we will apply one of these machineries that was cooked up for something else, but happened to work for manifolds.
But is it helpful to think of this SC as a ring? You can multiply polytopes with.
Well, but then you leave the dimension, right?
But it will be like a greater thing.
Yeah, you can think of this.
Yeah.
Yeah. I think they also thought about it. Yeah. Also for manifolds, there will be this analogy, and we didn't work that ring structure out. So yeah. So far we are only with disjoint union. So part 2. Let's go to SK groups. So what is SK? So SK is schneiden and kleben, which is exactly translation of cut and paste. But as I said, it was It was first considered here in Bonn by Matthias Kreck, and then other students of Hirzebruck, so I think it was Neumann, Ossa, and I probably forgot other people. So yeah, they played with this notion of SK for manifolds. So what is this? First of all, I want to fix dimensions, so n is fixed. And here it was reference for Rn, and now it's reference for dimension of the manifold. I always will stay in the world of smooth, compact, oriented manifolds, and I will not repeat these adjectives anymore. I will allow boundary. And with a very classical definition of Matthias, he considered only closed manifolds. And let me first hand wave the definition and then write something. So imagine you have some manifold and dimensional closed, not necessarily connected, and then you make a nice cut along codimension 1 submanifold. So you choose codimension 1 submanifold, you cut, and let's assume that now you have two connected components. So not every cut will give you two components, but this is my requirement. So I have to get two components, both have the same boundary now, and I choose any diffeomorphism of this boundary of one piece to another, and I glue back. And then declare that the manifold that I started is SK equivalent to second manifold, and this is called SK operation. So definition, SK operation means that I start with a manifold that can be written as gluing of two parts along some diffeomorphism phi.
Sorry, is the gluing the cut allowed to touch the boundary?
So right now we are in closed case.
Oh, we are closed.
Yeah. So first you are closed, right? But then I will talk about allowing boundaries. Yes. So and I go to manifold M prime with the same two pieces, but glued along another diffeomorphism. And if such two pieces exist, then I call this SK operation. And then we call two manifolds SK equivalent if n can be obtained from M by finitely many SK operations. So let's make some picture. So this is my M, and this is cut that I make. So this part, this upper part is M1, this upper part is M2, and what I can do, I can, for instance, glue this guy to this and this guy to this, and then this is equivalent to this is example. So what is obviously preserved by this? Well, okay, not obviously. It is preserved. It's Euler characteristic, and signature are preserved. By this operation.
Signature in the middle of knowledge.
Signature is a number.
On the middle of knowledge.
Yes. But that's a number, right? Like you can compute the same thing. Okay, so in comparison to this problem where people study very complicated groups, where you don't even know the set of these invariants under cut and paste, here groups are much easier, and only two invariants are signature and Euler characteristic in this case. So if you take any manifold, any two manifolds, and you want to ask yourself, are they SK equivalent? Then you just compute signature, you compute Euler characteristic, they coincide. Okay, then you know, then you can do it in finitely many steps. And so you also know what the groups are. They are very easy. So 0.
So sorry, this is true for every n, the signature and Euler characteristic are.
Yes. Yeah, so if there is no signature, so if it's not divisible by 4, then it's only Euler characteristic. Yeah, so it's 0 if n is odd, because Euler characteristic is also 0 in this case. Then it is z if n is 2 mod 4, and then it's z for z if n is divisible by 4. So this is a very classical story.
Can I ask one thing? So,
Yeah.
For these definitions, I could also work with topological manifolds, say?
Yeah, you could. So you should be a bit careful with scholars how you do everything back. But yes, there is no problem. You can choose any setup that you work at.
And the statement is the groups are the same, and in particular, every topological manifold is SK equivalent to this one.
Good question. I don't remember, but Kreck has it in his book. Yes. Okay, then
So technically, so there's group, so like group completion, right, of that thing. So because you find the equivalence class, and then after adding new things.
Right. I should have said this. Right. Like first I defined just equivalence relation, and now I want to take a group. Sorry, I was very slow. I should take a group with generators given by manifolds, group given by disjoint union, and a quotient out equivalence relation. Thanks. And then I want to do.
You dropped everything about connected components and so on that is said in words.
So sorry, it doesn't matter. We have connected components or not. So connected components here doesn't matter. It doesn't matter at all.
And to modify the here.
Say again? So no, I'm sure it's like it's not important. Adding connectivity or not, it's just not important here. So now I want to modify this definition a little bit so that I allow boundary. And it's not that I make my groups much more interesting. So I just want to preserve these two invariants. I want to have Euler characteristic and signature. But I want to make all the objects of the study to live in the same world. So in this case, somehow I have, for relations, I have manifolds with boundary, encoding the relations. And for objects, I have closed manifolds. So they're a little of a different nature. And now I want to have completely equal rights for all the manifolds. And let me say very briefly, so you could define exactly the same thing for manifolds with boundary, and the answer to one of the questions was, yes, I don't allow to touch boundary. So I take co-dimension one submanifold that is not touching boundary and that sits nicely and separates my manifold into connected components. And then I just write the same formula that I have SK boundary operation, where now I just allow manifolds with boundary and I glue back along the cut. So I never change my boundary. And if you want a picture, we could modify this picture and say, I have a hole here, let's say, and then this hole would go here. So this would be SK boundary equivalent manifolds. So let's observe what did we change. We changed that now we have more invariants and one extra invariant is boundary. No definition, just we remember that we have the same definition for manifolds with boundary. And now small lemma. So I claim that my old SK groups, they just sit injectively in this new one with boundary. So hypothetically, when I add these new relations, allowing pieces with boundary, I could have added more relations to here, but this doesn't happen. And
Julia, can I quickly ask, is this the 3 billion group generated by manifolds in the new model of SK, or is this just...
Yeah, a billion group generated by all the manifolds. And then I take a boundary of a manifold. Maybe it's not good, but like boundary. And then what is this? So if I have a boundary of some manifold, it's manifold on one-dimensional order, and obviously it's null border. So this group is subgroup of Grothendieck group of all n-1 dimensional manifolds, closed, so without boundary, generated by null border manifolds. And here I take different class. So now we know that this new group is a huge one, which is small part given by this SKN. And I claim that this group is free, so this sequence splits. And I have this huge chunk that corresponds to different classes of null bordered manifolds. So what I achieved, I only achieved that now I can allow all the manifolds with boundary, but I pay the price that now I have this huge group. What is important for us is this piece. So 2 invariants, Euler characteristic and signature. And now we are ready to go to the next part.
So you insist that not to fill in the boundary, right? So you insist to keep it, but
Yes.
it's very tempting to start filling it in.
Yes, I know, but no. We insist that we keep boundary and we don't touch it at all. So next part, it is called K-squares theory. It's like for a moment, for 5 minutes we forget about what I said. It's just machinery that's applied to some abstract category, and then I will tell how I apply it to this, but now it will be a little unrelated. So the setup, the input for this machinery is a category with a notion of squares. So C is a category. Let's say with initial object. So this is a little extra condition. It's not unnecessary, but in our case it will hold. So let me just say that we want this. So category, the notion of 2 subcategories of morphisms. And this is just notation for the arrow. So you shouldn't think about Waldhausen category where you see cofiber maps and cofibrations. So these are just 2 notations. So these are 2 subcategories of morphisms. And C. And then I have one more piece of the data, which are squares. And squares are diagrams that are shaped like squares, where horizontally we allow one type of zero, and vertically we allow another type of zero. And this is given as a set of such squares. So not all squares of this shape are squares like this, but some of them. And we choose which squares are, and they should satisfy, of course, some properties.
Square is referred to the unit.
Yeah. This is one of the properties. So yes, squares are commutative, so this is like real, honest diagram. And then you require certain things. For instance, squares compose horizontally and vertically. What this means, it means if I have to square that degree on this edge, then the whole thing is also a square from my set, the same vertically. Then I require, this should be probably set for C, so it's with initial object and coproduct. So I want my category to have coproduct. And I want some other conditions, but it's a little strange to maybe to state them now. I will tell you the construction, and you will see what kind of conditions you need. So I put 3 dots, but you really will be able, after I tell you the construction, to recover these 3 dots. And now construction. I have some category with this data, and I construct a bisimplicial set. I call it B. And I should tell you what the set of KL simplices. So KL simplices. And these are all the diagrams of size KL that consist of squares. So for instance, this is 1, 1 simplex. This is diagram of size 1, 1, and it consists of 1 simplex. If I want 1, 2 simplex, it will be diagram of this shape.
Commutative ladders.
Say again?
Commutative ladders.
Yes. Yes. And this is my definition of bisimplicial set. And now you remember that bisimplicial or simplicial, whatever, it requires certain conditions that you should have trace maps and degeneracy maps, right? And for instance, what I told you, squares should compose vertically and horizontally. It's exactly conditioned for the face map, because I guess it is kind of obvious that face map should be deleting corresponding row or column. It's the only natural way to proceed here. And for this just for this to be defined, I have to compose squares. Like I delete, but I want to remember what was there, so I compose. So this is this condition. Then if I want degeneracies, I want to write something like equal. So I want some squares that look like I have some non-trivial error here, but then I have equalities here. So I also encode it in the data of my category with squares. So these 3 missing dots are exactly everything that you would need to make this construction a really bisimplicial set. And one extra requirement was coproduct, and this is coming later. Why do I need coproduct? I have this bisimplicial set, and then I define K square of category C to be loops on geometric realization of this bisimplicial set. So what I wrote is a space but it is given co-product, it is an infinite loop space. So this is a spectrum. And why do I take loops? Because if I just take geometric realization here, with condition of initial object, the space is just connected. So my first homotopy group, zeros, would be completely trivial, so very boring. So I shift. So this is the only thing needed. And that's a construction. But why does it dare to be called K-theory? And here is an explanation. If C was Waldhausen, and I remind you that in Waldhausen category we have this co-vibrations, then I want to turn C into category with squares. And how I do it? I want to specify two subcategories of morphism in C. And first type of arrow is exactly co-vibrations. Well, it's a little stupid to write, but this arrow is co-vibrations, yes, in Waldhausen. And the second type of arrow is all. So it's all maps. And what are squares? So squares will be diagrams of this shape. And I say those diagrams that are push out up to weak equivalence. Okay, so not push outs, but push out up to weak equivalence. And if you take Waldhausen's theory of C, and let's say you take S construction, then you will get equivalent result to taking square construction to this C square. So this construction indeed deserves to be called K-theory. Oh, I have some space there. And it does one very nice thing on Phi naught. So K naught, which is just zeroth homotopy group of this space or spectrum. Oh, sorry. It has a very nice presentation. So it's a abelian group generated by objects of category squares, and then you mod out A plus what? Plus G equals B plus C for all squares that are part of this data. Now it is time to apply this for manifolds. And they claim that using this construction with quite natural, very natural choice of a category, you will get a spectrum that gives SK groups. And moreover, it is related to algebraic K-theory of integers in a very natural way.
Varieties can be obtained this way?
I guess this is what they were doing initially. Yes. Exactly, yes.
And what are the inclusions and surjections? Inclusions and surjections?
For varieties? I don't know.
All
Okay, yeah. I think it's the convergence of blowdowns. Yeah.
Okay. So next part, application. Escape. And now our category is category of manifolds with boundaries, smooth, closed, oriented. Both subcategories of these arrows, they are just embeddings, both of them. So even though they denote it in a different way and they play different roles in the construction, I can take them to be the same. So these are embeddings of manifolds. Such that boundary of M such that every connected component of the boundary either entirely lies in the interior. So let me make some pictures. So this is M. And this is M prime. And this is one connected component of the boundary, and it goes here, and this is another, and it goes here. This is allowed, and this is my condition. So every connected component of the boundary either goes entirely to the interior, or entirely to the boundary part of M. So what is not allowed, it would not be allowed to do something like this boundary would go first to some part of the boundary, jumps and goes back. So this is bad, this is not allowed. Everything else is allowed. And squares, they are just commutative squares such that they are push-outs in the category of spaces. As space. So again, what is allowed and what is not allowed? It is allowed to glue something and you really have to take push out and nothing weird. So for instance, if I write square and then some sphere here, it is a commutative one, everything is embedding, but this is not a push out. So this is bad, and the white one is good. And then with this notion of category of squares on manifolds, I claim, so this is a theorem now, and this is theorem with 5 authors. Hausdorff, Merlin, Murray, Rovi, sorry for not writing all the names fully, and myself. So this theorem is saying that what I just defined is a category with squares. So we can produce K-theory spectrum out of it. Then, so first part. Second part, we can compute zeroth homotopy group, and it is exactly SKN with boundary. can relate it to algebraic K-theory of Z of integers. And the map is quite easy. So let me first say that I go to square K-theory of chain complexes over Z that are homologically bounded and consist of, homologically bounded for me means a chain complex that has finite homology and at every degree it is finitely generated. On the level of categories, it is just sending object M to singular chain complex of M. And then here, this is Waldhausen category. So I can just view it as Waldhausen category of chain complexes. And at the same time, it is usual K-theory of that. So it's not that I directly go from here to K of Z, I have to go via chain complexes, but standard thing to do, right? And then, since we know K naught, so what happens on K naught? So on K naught, this thing is SKM, this boundary, and this is just Z. And I know the generators here are classes given by manifolds, and it goes to all the characteristic here. So we constructed a map from K squares of manifolds to K of Z, which take class in SKN and sees its Euler characteristic. So this is first part. Then we can say something about K1.
Can I ask one thing?
Yeah.
Can you replace this manifold boundary N or so with something like just CW complexes and cellular inclusions or so?
Yes, and it will be something like A theory, right?
Yes. And this thing just maps to A theory?
Yes.
By the inclusion, and this map factors to that.
Right.
That process.
So it maps to A theory, but what factors to what?
The map from manifold boundary to chain complexes.
It factors through A theory, yes. Yes. Let me write this, right? Yeah. So this construction is very similar to A theory, but since we restrict ourselves to manifolds, potentially we can get something very different, right? Like already on K naught, it sees signature. So what Marcus just said, so he said, let's look at K squares of manifolds. And yes, we have A of point. And then this has also a map, which is K of sphere spectrum. This has a map to K of Z. And this map is very easy as well. So this is Waldhausen, this is K theory of Waldhausen, so it can be turned into a K squares of this construction. And the map is just sending manifold to manifold is joint union point. So this is just a very stupid map, but it works. That's correct. And yes, on the other hand, this is just this map, right? So also with this observation, we can get that sphere spectrum is a direct summand of this. So sphere spectrum splits as direct is a direct summand. Right. So like an A theory, it is sphere spectrum plus difficult part, It's the same here for k squares, sphere spectrum plus another difficult part. And potentially it also, it says that all higher groups are at least non-trivial because it has homotopy groups coming from sphere spectrum. But we have very explicit result about elements in K1. So this is due to Mona, George, and myself. So here, what we can say is that every pair of a manifold and self-diffeomorphism of a manifold, it gives an element in K1 of our spectrum.
So here a manifold may still have the boundary, right?
Yes, 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 yes. But here I want to take manifolds without boundary. So for manifolds with boundary, it also gives an element in K1, no problem. So the first part of the sentence still holds. But then I want to say something about this element. So I want to say where it is mapped in K1 of Z explicitly, like I will tell you the number where it goes. So this is Z2, right? This is Z2. And I want to say, like, this is this map that I just took, and I will tell you, like, what is this number. So now I will make a small table, and now I say that the manifold is closed. And I'm sure we can work it out for manifold with boundary, but it's just a little more difficult. So it depends on dimension of M, and if F is orientation preserving or reversing. So two cases, odd even is an orientation preserving, orientation reversing. And if I don't look it up, I will confuse. So in this case, it's for and for me, the 2 is viewed multiplicatively. So it's plus minus 1, plus 1 is trivial, minus 1 is interesting. 1, so this is boring, but here it's very interesting. It's a semi-characteristic of M. Here it's also interesting. If I take F, it induces something in the middle dimension, and I call it Fk on the homology of the middle in the middle dimension. And this invariant computes determinant of this map. And here it's product of these two.
Yeah, could you raise it more?
Yes. Yeah. So it's semi-characteristic, and it just says that you take even Betti numbers. Mod 2. So usual order characteristic is some alternating sum of Betti numbers, and here you just take even. Or in other words, you just take half of those, right? Up to middle dimension.
So it's minus 1 to that.
It's mod 2.
2. No, but you want plus minus 1.
Oh, sorry, yes. Okay. You understood. And then I translated to plus minus 1. And 2 more minutes before I finish. So far, these are the results on K0, K1. So here I would have said like sphere spectrum splits, probably bigger chunk splits, bigger suspension thing splits, but this we can't, we didn't work it out yet, so I don't claim anything. And there is one more fun application of this squares construction. So let's go one step further and kill even more elements in these SK groups. And it was also studied by Matthias. So they are called, there are groups that are called SK bar group. And this is, it also depends on n. It is SKN. I don't write boundary because I want to tell classical thing first. And I mod out cobordism relation. So coordinate manifolds, they are also considered now the same. So what I just did, I still preserve the signature, but I completely killed Euler characteristic. So this is the group that only sees signature. And we can do the same analog for this with boundary. But now we have to explain what it means to be coordinate for something with boundary. So there is a notion of cobordism with boundary, where you allow whatever happening on your boundary, and then it's a very bad notion for us, because all two manifolds with boundaries, they are coordinate. And how you see this? So you take a manifold with boundary, you take cylinder, and you collapse the boundary. And you use this as an object, and this as part of your cobordism. So the picture will be, and then it says any coordinate or any manifold is coordinate to empty. So very, very bad for us. So we restrict to those cobordisms that on the boundary are trivial. Trivial means they are cylinders, diffeomorphic to cylinder. And then I define SKN with boundary as my SKN boundary modulo cobordisms that are cylindrical on this part, on the boundary. And then we thought that this should also somehow fit into this square thing. But with squares it wasn't enough to encode all this relation, but cubes work. So if you add one more simplicial direction, then you are exactly able to do this. And now I will, in 1 minute, I can hand wave the construction of the spectrum and then I finish. So now instead of having bisimplicial set, I will have a trisimplicial set where my building blocks are not squares, but now they are cubes. And I will just describe to you what a cube means. So for cube, again, I will have a push out of manifold. So on this face of the cube, it is the same data. So it's M0, M1, M2, M3. So these are push outs in spaces. But then I want to, in this third direction, I want to encode coordinates. So this face, front face, is our old square, and the other face will also look like square. But in between, I will encode coordinates. And cube also should include data of inclusion of coordinates. So it's a data of 4 manifolds. Here, 4 manifolds there. Both faces fit into push-out squares. And it's also data of 4 coordinates. And on coordinates, it also should be push-out. And then I define the same way as before trisimplicial set, where I, j, k cubes should be combination of these cubes. And again, I claim this is a spectrum, and on k naught it encodes these groups. Okay, and here, okay, thank you.